Okay, I've got argon in a piston cylinder assembly. It's compressed isentropically from state 1 to state 2. Okay, assuming ideal gas and constant specific heat ratio of 1.67, which is true because it's argon, which is a monatomic gas. I want to find the second temperature and the work in kilojoules per kilogram. So, because this is an isentropic process, and because it's constant specific heat, I'm going to use the relationship for adiabatic for a polytropic process with constant specific heat. Now again, this I can only use when I have constant specific heat like I do with argon. Okay? And because it's isentropic, it's also adiabatic, so I just substitute in the specific heat ratio in for K. Which again for this one is going to be 35 plus 273 and plus wait a minute, sorry about that, other way, it's going to be T2, which is what I'm looking for, over 35 plus 273 equals P2, which is 300, over P1, which is 150, to the 1.67 minus 1 over 1.67. From this, I get T2 equals 407K, which equals 134 degrees Celsius. Okay? So that's how I find that second temperature. Now, also, you'll remember in the book we talked about polytropic process, we have the work equations, which is what I'm trying to find here, for polytropic processes. And that work equation is nothing more than work equals CV times T1 minus T2, where I've got the mass times the specific heat ratio, specific heat, T1 minus T2. Where CV, we also have this relationship that we talked about back in chapter 3, which is R divided by K minus 1. Okay, where R is 8.314 divided by 28.97. Oh, that's not right. For argon, molecular weight of argon we can look up. I'll let you do that on your own, and I actually get it to be 39.94 for the molecular weight of argon over 1.67 minus 1. Right? So that's what CV equals. So I can plug that in and find my work, where the work is work per mass, which is what I'm looking for. Okay, is that, and I'm going to just go ahead and write it again, 8314 divided by 39.94 divided by 1.67 minus 1. Again, that's the CV times T1 minus T2, where T1 is 35, T2 is 134, and I actually get the work equal to negative 30.8 kilojoules per kilogram. So again, I can use this stuff because it's argon, so the specific heat is constant at 1.67. An isentropic process is also an adiabatic process, where it's also a polytropic process where N equals K. So using those polytropic relationships, I can find temperature using this equation, and I can find the work using this equation because it's a constant specific heat adiabatic / isentropic process. I can use those two. And that's how I find T2 and the work.